Good morning. So can you hear me? Hello, can you hear me? All right, so let's start. So let's recall last time we talked about the one of the theorems is the remainder theorem. So the remainder theorem says that if we have two integers, and let b be a positive integer, then there exists two numbers, two integers, q. There exist integers q and r, so that A is equal to B times Q plus R, and R is between 0 and B. So moreover, such Q and R are unique. Okay, so recall the key for this theorem, as we mentioned, is the remainder R is between 0 and B. Okay, so today we're going to talk about a very famous theorem called the Bethel's theorem, which says that the greatest common factor of the two integers can be written as a linear combination of these two integers. So before we say the theorem, let's first look at the definition of linear combination. Okay, so a number C is a linear combination of two integers A and B if there are two integers.
Hi, can I have a sausage McMuffin, a hash brown?
Two integers S and T, so that C can be written as S times A plus T times B. Okay, so you can find the integers as S and T so that C is equal to SA plus TB. All right, so let's look at some simple examples. So the number 16 is a linear combination of 2 and 3. So why? This is true. So we can write 16 as, so 2, okay, 5 times 2. So 5 times 2 plus 2 times 3. So here, this 5 is S and 2 is T. Okay, so this is clear. And on the other hand, the number 21 is not a linear combination of 2 and 4. So can anyone tell me why 21 is not a linear combination of 2 and 4? Okay, so why 21 is not a linear combination of 2 and 4?
Is it because the linear combination of 2 and 4 will result of an even number?
Okay, good, very good. Exactly, because the linear combination of 2 and 4 is an even number because both 2 and 4 are even numbers. So 21 is an odd number, so an odd number cannot be equal to an even number. Very good. Okay, so this is because a linear combination of 2 and 4 is even. Okay, so this is the basic example of linear combinations. Okay, so as I mentioned in the beginning, so one of the famous theorem about the greatest common divisor is the linear combination of the original numbers to represent the greatest common divisor. Okay, so this is Bizarre's lemma. So which said that the greatest common divisor up to integers is a linear combination of those two numbers. So that is, there exist integers S and T so the greatest common divisor of A and B is equal to S times A plus T times B. Okay, let's, before we prove this lemma, let's look at an example. So for example, the greatest common divisor, say, of 2 and 3. So 2 and 3 are coprime. So this is equal to 1. And then it's easy to see that this greatest common divisor 1 is equal to -1 times 2 plus 1 times 3. Okay, so 1 is a linear combination of 2 and 3. And then if you look at the greatest common divisor of, say, 9 and 24, so the greatest common divisor of 9 and 24 is equal to 3. And how to write 3 as a linear combination of 9 and 24? So we have a 3 times 9 plus -1 times 24. Okay, so another thing you want to pay attention is that this representation may not be unique. There could be different ways to represent the greatest common divisor. For example, in the first example, this 1 can also be written as -4 times 2. This 1 is also equal to -4 times 2 plus 3 times 3. And what is this 3? This 3 can also be written as so say 11 times 9 plus say -4 times 24, for example. So you can see not only you have a representation of the greatest common divisor as a linear combination, you have different ways to represent this greatest common divisor. Actually, it can be shown that the greatest common divisor has infinitely many representations as the linear combinations of the original two integers. All right, so now next, let's look at the proof of the Bezout theorem. So the greatest common divisor is a linear combination of the original two numbers. All right, so let's look at the proof. Okay, so if A and B are zero, then by our definition, the greatest common divisor of A and B in this situation is going to be 0. Then, and of course, 0 is going to be equal to, you can pick any number, say 1 times 0 plus 0, 2 times 0, whatever. So this is okay. All right, so in the case when both A and B are 0, this is okay. So we may assume that at least one of the A and B's are not equal to 0. For example, A is not equal to 0. So the case for B equals to 0 is the same. It's assume one of them. Okay, now we define a subset of the natural numbers. So we define this L of AB to be the set of all linear combinations of A and B. That is M times A plus N times B, where Mn are integers. And of course, this set is long empty, and we'll let L plus AB to be the set of all numbers. So that is C belongs to L of AB, and C greater than 0. So L plus of AB are the numbers in L of AB which are positive. So the first thing we want to claim is L plus is not equal to is not empty. So first, we notice that L plus of AB is non-empty. empty. So why L plus AB is non-empty? Because we assume A is not equal to 0. So we can just pick, so if A is greater than 0, then we know that A itself is equal to 1 times A plus 0 times B is in L of AB. So A is also in L plus of AB because A is greater than 0. So if A is less than 0, then negative A, which is equal to negative 1 times A plus 0 times B, this is also a member of LAB. And since in this case, negative A would be greater than 0, so we have negative A is in L plus of AB. All right, so this shows that L plus of AB is non-empty. So, and since L plus of AB is non-empty, by the basic properties of natural numbers, any non-empty subset of the natural numbers has a smallest number, has a minimum. Okay, then we are going to show the minimum is actually equal to the greatest common divisor of A and B. Okay, so let me write here the L of AB is a set of all linear combinations and L plus of AB is equal to the number C belongs to L of AB and C greater than 0. Now, since L plus of AB is a subset of the natural numbers, there exists, okay, and also non-empty. Non-empty, there exists a minimum of L plus of AB So we denote it by D. Okay. So this, because D is a member of L plus of AB, so D is equal to some S times A plus T times B for some integers S and T. Okay, now since, so we're, for the simplification of notations, we'll let G be the greatest common divisor of A and B. The greatest common divisor is clearly a divisor. So we have G divides A and G divides B. Hence, G divides S times A and G divides T times B. Because S times A is a multiple of A and T times B is a multiple of B. Now, since G divides SA and G divides TB, therefore, G divides the linear combination, the sum of these two numbers. So that is G divides D, because D is equal to SA plus TB. And since both G and D are positive, so last time we proved that the greatest common divisor is always positive, and D is a member from L plus of A and B. L plus consists of all positive numbers, positive linear combinations of A and B. So both G and D are positive. Now, G divides D implies that G would be less than or equal to D. Okay, so we proved one thing, G is less than or equal to D. In order to show G is equal to D, so we want to show the other direction, that is D would be less than or equal to G. To show G is equal to D, it is enough to show that D is less than or equal to G. Okay, now here we want to use the remainder theorem. actually, how to use the remainder theorem? We would like to show that D is actually a divisor, a common divisor of A and B. And if we can show D is a common divisor of A and B, because G is the greatest common divisor, then we can claim that D is less than or equal to G. We'll prove that D is a common divisor of A and B. Remember, we proved the theorem last time. If D is a divisor of A, then the remainder of A divided by D would be 0. So we just want to show the remainder when you divide A by D is 0. Similarly, you can show that the remainder of B divided by D is also 0. Okay, so by the remainder theorem, so we can write A is equal to this D times Q plus R, with R between 0 and D. Okay, you should remember as so what we get is R is equal to A minus DQ. And remember, this D is a linear combination of A and B. So this D is S times A plus T times B. This is how we choose this D is from L plus of AB. Okay, so this is what we have here. If you remember, this D is equal to S times A plus D times B. Okay, if you rewrite it, then this is 1 minus S times A plus negative TQ times B. Okay, what we actually get is that, so that is R is equal to 1 minus S times A plus negative TQ times B. This means that R is a linear combination of A and B. So R belongs to L of AB, a linear combination of AB. But notice that R is less than D, and D is the minimum in L plus. Hence, since D is the minimum, of L plus of AB, then this R has to be 0, because R cannot be positive. If R is positive, then R itself belongs to L plus, and R is smaller than D. This contradicts with the minimality of D. So R is 0. Okay, so R is 0, which means, therefore, A is equal to D cubed, okay? Because here R is 0. And D divides A. Okay, a similar argument, so similarly, D divides B. So the proof is essentially the same. Hence, D is a common divisor of A and B. Now, since G is the greatest common divisor of A and B, so we know that D would be less than or equal to G. Okay. All right, so we proved that G is less than or equal to D, and now we showed that D is less than or equal to G. Therefore, D is equal to G. But remember, D is the linear combination of A and B. Hence, G is equal to S times A plus T times B. Because D is equal to S times A plus T times B. So this finishes the proof. So roughly speaking, the idea here is that you first look at the set of all linear combinations of A and B, and you take out those positive linear combinations. And the minimum of the positive linear combinations of A and B is exactly the greatest common divisor, okay, of A and B. Yes. On the third line, just L of A and B. Yeah, I just want to claim R is a linear combination of A and B. Okay. Okay, one corollary of this theorem is the set of all linear combinations of A and B equals to the set of all multiples of the greatest common divisor of A and B. So let's look at a corollary. Of all linear combinations of A and B equals the set of or multiples of the greatest common divisor of A and B. Okay. Recall, to show two sets are equal, you want to show one set is contained in the other and the other set is contained in the original one. Okay. So let's look at the proof. So first, if we take an element from the linear combination of A and B, we want to show it's a multiple. So let's say S times A plus T times B be a member in L of AB. Okay. Since, okay, we still let G be the greatest common divisor. So let G be the greatest common divisor of A and B. Then G divides A and G divides B. So what we have is G would divide S times A and G divides T times B. Hence, we have G divides S times A plus T times B. So you can claim S times A plus T times B is a multiple of G. All right, this is one direction. We showed that any linear combination is a multiple of G. So on the other hand, okay, let K times G be a multiple of G. So by Bezout's theorem, G is a linear combination of A and B. So K times G would be K times S A plus K times T times B is a linear combination of A and B. Okay, this finishes the proof. So any multiple of G is a linear combination of A and B. So that shows the set of all linear combinations of A and B is exactly the set of multiples of the greatest common divisor of A and B. Okay, so the next lemma tells us that if A divides the product of two numbers B and C, and A is a coprime to one of the numbers, then A has to divide another number. So here's a statement of the lemma. if A divides B times C, and A, B are co-prime, then A divides C. Okay, so let's look at the proof. Since A, B are co-prime, so co-prime means the greatest common divisor of A and B is equal to 1. So this is the equivalent definition. Now, by Bitzel theorem, so the greatest common divisor of A and B is a linear combination of A and B. 1 is equal to S times A plus T times B. Okay? This is because the greatest common divisor of A and B is equal to 1. Now, if we multiply this equation by C, multiply the equation by C, multiplying, we get C is equal to S C times A plus T times B C. Okay, you multiply a C. Okay, now since A, of course, divides S times C times A, and A divides T times BC. The reason is because our hypothesis tells us that A divides BC, so A divides T times BC, okay? Then A divides SC times A plus T times BC. Okay, the sum of two multiples of A is still a multiple of A. But SC times A plus T times BC is equal to C here. So A divides C. So one thing I want to address here is that the condition A and B are co-prime is important. You cannot remove this condition. For example, if you look at 6 divides 4 times 9, however, 6 does not divide 4, and 6 does not divide 9. So you see the main reason is 6 is not co-prime with 4, and also 6 is not co-prime with 9. So that lemma doesn't work. So six and 4 is not equal to 1, and the greatest common divisor of 6 and 9 is also not equal to 1. The lemma is not valid. So you understand this condition called prime condition is needed. So as I mentioned earlier, that the greatest common divisor is a linear combination of A and B, and also the representation, you have infinitely many ways to write the greatest common divisor as a linear combination. So here's the last lemma we're going to prove today. Let A and B be integers. So let C be a member in L of AB. C is a linear combination of A and B. Then the equation S times A plus T times B equals to C as infinite many solution pairs ST so which has the form S is equal to S0 minus J times B divides G. And the T is equal to T0 plus J times A over G. So where S0, T0 is a particular solution pair, and G is the greatest common divisor of A and B. So in other words, what this lemma tells you, okay, so any number which is a linear combination of A and B has infinitely many representations, and each representation is just a particular representation as 0, T0, and subtract or plus a J times B over the, or A over the greatest common divisor of A and B. So we should remember that a linear combination of A and B is just a multiple of G, the greatest common divisor of A and B. Okay. So to prove this, we'll show two things. The first thing is to show that any pairs S and T of the form is actually a solution of the equation. And second is if we have any solution of the equation, we can always write this, the pair ST in the form. Okay, so let's look at the proof. We first show that such pair S and T is a solution of the equation. Okay, so we just plug in S and T into the equation. So plug into the equation, you get S, let's compute S times A plus T times B. This is equal to, okay, S0 minus J times B over G times A plus T is equal to T0 plus J times A over G times B. Okay, so this is equal to, so S0 times A plus T0 times B and plus negative J times AB over G plus J times AB over G. Okay, so the first part, the parenthesis, because S0, T0 is a particular solution. So the first part is just equal to, this is equal to just C. Now the second part is 0. This is 0. This is 0. So the whole thing is just equal to C. So this shows that S and T of the form is indeed a solution for the equation. So what we really need to justify is any solution of the equation has the form. All right, so let ST be a solution of the equation S times A plus T times B is equal to C. And we also know that S0 is T0 is a particular solution, so we know that S0 times A plus T0 times B is equal to C. Subtracting two equations, so subtracting these two equations, we get S minus S0 times A plus T minus T0 times B is equal to 0. So this implies, so what we get is T0, T minus T0 times B is equal to S0 minus S times A. we just move s minus s0 times a to the right-hand side. So you get this equation. Okay, now if you look at here, we can divide the greatest common divisor of both a and b. So dividing. So dividing g, we have t minus t0 b over g is equal to s0 minus s times a over g. So since g is a divisor of a and b, you know that b over g and a over g are integers, so they are still integers. And since the greatest common divisor, so we proved last time, b over g and a over g is actually equal to 1. Okay, g is the greatest common divisor of a and b. When you divide g, we proved last time that the greatest common divisor of a over g and b over g is 1. Actually, they are co-prime. And you also know that b over g divides s0 minus s times a over g, because this because t minus t0 b over g is equal to s minus s0 times a over g. So b over g divides s0 minus s times a over g. So by the previous lemma, so when an integer divides the product of two integers and the integers co-prime with one of the product, then you know this b over g would divide s0 minus s. So what does this mean? This means, so there exists a j in Z such that S0 minus S is equal to J times B over G. Hence, S is equal to S0 minus J times B over G. So when you plug into this equation, plug into S equals to S0 minus J times B over G into this equation. So plug into, so suppose this is star. Plugging into star, you get T minus T0 B over G is equal to S0 minus S is J times B over G times A over G. Okay, because S0 minus S is J times B over G. Now, the B over G can be canceled, and T minus T0 is equal to J times A over G. Therefore, T is equal to T0 plus J times A over G. Okay, so this finishes the proof. So any solution of the equation is of the form S equals to S0. Here, S equals to S0 minus J times B over G, and T is equal to T0 plus J times A over G. Okay. So now we know that any linear combination of A and B has infinitely many representations. So do you have any questions? Okay, so since we've already had a lot of proof today, it's pretty dense. Today I'm going to stop a little bit earlier. So if you don't have questions, then I'm gonna stop it here. And also I'm going to assign homework today. So please check back late tonight or tomorrow. And we're done today. Yeah, bye-bye.